Hi, my name is Larry Johnson, and I'm going to be demonstrating the friend pairing problem using dynamic programming. So, this is the problem. Given a group of n friends, each can pair up with another friend or remain single. They can only be paired once, and given these parameters, calculate the total number of ways in which the friends can remain single or pair up. So basically, we're just trying to show how a number of friends can group or pair up, and they can only pair up one time, and only with one person. So for a group of 3 friends, just for example, we can all remain single, or 2 people can group up, and one of the unlucky people would remain single. So you have the first situation, which is they're all single, and then the 2, 3, and 4 is where different people group up and one person stays single. And so for the input of 3, you get a total of 4 different possibilities. And this is just an example situation. For something like 4 friends, it would have 10 different possibilities, or maybe 5 friends would have 26. So let's see how we would maybe solve this situation. Okay, so similar to the Fibonacci sequence, the Fibonacci recursive problem, we have this formula here, which is representative of how the friends get together. So let's explore this formula here and how we get to that. So the only possible orderings that we can have are if all the friends are single, right? This is the first situation we had here. Or if the first person is single, every other pair or every other friend is paired contiguously, right? So we will go through them, and we will have the first person being kept single, right? And then xi, for example, so the next friend on would be kept single, and then the next friend on would be paired with another provided. So we're thinking about we're trying to like partition down each tier of the tree, and we're trying to find the person who will remain single in this part of the group, and grouping each subsequent friend after that, right? And then on this side of the tree, we're just thinking about the situation in which everyone is single. So that's kind of how we get to the situation, right? So on the left side, we have everyone remains single. And then on the right side, we have the situation in which we're grouping. So this creates a tree. So let's look at the tree in which we had for our first situation, right? So we had a group of 3 friends. So we have a function of 3, and we're going to split this into our little formula here. So we have f of n minus 1, which is 2, which is here. Then we have n minus 1, which is 2, times f of n minus 2, which is f of 1. And because f of 1, it's only going to be one friend at this point. One friend can only be ordered one way. So we already have the right side of the tree completed right here. It's just 2 times 1. Now let's go back to the left side of the tree. F of 2 gets plugged right back into this formula again. We have f of 1. Like I said here, one friend can only be ordered one way. And then we have 1 times, this is the same formula over here, 1 times f of n minus 2, which is f of 0. And we're just going to say that's 1 again, right? Because 2 friends can either remain single, so we would have, for example, 1 and 2, and they can remain single, or they can remain grouped. They can group up. And so that's just what this represents. So we have 1, 2, and then 3 and 4, which is exactly what we found here. And we can make this tree much bigger and much more complicated, because the tree has a lot of overlapping subproblems. Now, because there are a lot of overlapping subproblems, we can use something called dynamic programming. And we could save a lot of time because we can have all the values calculated and saved for future reference. And this is really easy to do with an array, right? Because we can have just an array of like a big slot, or a big group of slots in which we plug in the values for the subproblems that we've already done. Let's say that that array is called return, and we're just creating it as a big value for the amount that we want to find, for the amount of friends that we want to find. We're going to cycle through the array. We're going to cycle through the group of friends, starting at 0. And right here, we're just going to try to fill up the friends starting at 0 and going to 2. We're just trying to fill up these first values because we know for a fact, right, that 0 is going to be 0, that 1 is going to be 1 because one friend can only be grouped one way. 2 friends can be grouped either they're both single or they're paired. So we know these values. It's kind of similar to how Fibonacci has like seeding values where it's like 0, 1, 1. We know that this is going to be 0, 1, and 2. And then this is where the magic happens. We're going to apply the formula that we derived earlier, and we're going to have each value, each subproblem equal different little subproblems here in the formula, which is back up here. Yeah. So let's think about 3, right? This is one we're kind of like continuing through. We've already made sure that we know return of 0 equals 0. We have return of 1 equals 1, return of 2 equals 2. Now we're at return of 3. So we're at return I3. We've cycled through 4 times now, but we're at 3. And so we say return of 3 minus 1 is 2, which we're looking back here, that's true. And then we have I minus 1, which is 2, and we have return 1. And the cool thing is we already have 2 and 1, right? So we know exactly what this value is, and we know exactly what this value is, and so we can compute that, and we could say return of 3 is 4. And then when we go back through again, we have return of 4. We can know that this value right here, which is return of 3, we know that exactly that number is actually just 4. And then after that's all cycled through, we've gotten all the way up to the top of the friend group, because we're going from bottom up. We started at the bottom and then we got up to the top. We can return the actual, we can return the number at that at the index that we wanted to find. This leaves us with a time complexity of big O(n), because we cycled through the group from bottom to top of the friend group, but we've only went through it one time, right? So it's just big O(n). And then space complexity big O(n), because we have an array here, and we're going to be filling up that array with the amount of friends that we're looking for. And this is much better than the brute forcing time complexity, right? Because, like I said, 3 was 4, 4 was 10, 5 was 26. We're looking at something exponential here. Where every time we want to do a problem, we have to do many, many different little subproblems underneath it. And those subproblems have their own subproblems, and those subproblems are copied over and over again. So we're doing a lot of excess calculations in the brute forcing algorithm, which is avoided because when we use the pseudocode, we have only the values that we need, because we can go back and refer to them later. These are some of the references I used, and thank you.